Introduction to data analytics. Data analytics involves examining raw data to uncover trends, patterns, and insights that can inform decision-making. It is a multidisciplinary field that combines statistics, computer science, and business knowledge to solve complex problems. The primary goal is to extract valuable information from datasets, enabling organizations to optimize processes, predict future outcomes, and gain a competitive edge. Understanding the fundamentals of data analytics is crucial in today's data-rich environment. This course will build a strong foundation, moving from basic concepts to advanced analytical techniques. Professionals across various industries are increasingly relying on data-driven strategies. The importance of data analytics spans across virtually all sectors, from healthcare to finance, and retail to manufacturing. Businesses leverage analytics to understand customer behavior, improve operational efficiency, and develop new products and services. Governments use it for policymaking, resource allocation, and public service improvement. Scientific research heavily depends on data analysis to validate hypotheses and discover new phenomena. This diploma aims to provide a holistic view of the field, preparing learners for real-world challenges. Data analytics lifecycle stages. The data analytics lifecycle typically involves several distinct stages, beginning with business understanding. This initial phase focuses on defining the problem, understanding project objectives, and identifying key stakeholders. It's crucial to clearly articulate what questions need to be answered and what business value the analysis is expected to deliver. Without a clear understanding of the business context, even the most sophisticated analysis can fail to provide meaningful results. This stage sets the foundation for all subsequent activities, ensuring alignment with organizational goals. It involves extensive communication with domain experts. Following business understanding, the life cycle proceeds to data acquisition, data cleaning, exploratory data analysis, modeling, and finally, deployment and communication. Each stage is iterative, meaning analysts often revisit previous steps as new insights emerge or challenges arise. Data acquisition involves collecting relevant data from various sources, while cleaning addresses inconsistencies and errors. EDA helps uncover initial patterns, and modeling builds predictive or descriptive models. The final stage focuses on presenting findings and integrating solutions into operational systems. This structured approach ensures thoroughness and accuracy in the analytical process. Statistical foundations for data analytics. A strong grasp of statistics is fundamental for effective data analytics, enabling analysts to make sense of data and draw valid conclusions. Descriptive statistics summarize and describe the main features of a dataset, providing simple summaries about the sample and its measures. Key concepts include measures of central tendency, like mean, median, and mode, which indicate the typical value in a dataset. Measures of variability, such as standard deviation and variance, describe the spread or dispersion of data points. Understanding these concepts is essential for initial data exploration and reporting. They form the bedrock for more advanced analyses. Inferential statistics, on the other hand, allows analysts to make predictions and inferences about a larger population based on a sample of data. This involves techniques like hypothesis testing, where a claim about a population parameter is evaluated using sample data. Confidence intervals provide a range of values within which the true population parameter is likely to fall. Regression analysis, a powerful inferential tool, examines the relationship between variables. These statistical methods are critical for moving beyond mere description to predictive modeling and decision-making under uncertainty. They are indispensable for drawing generalizable conclusions. Probability theory for data science. Probability theory is a fundamental branch of mathematics that deals with the analysis of random phenomena, providing a framework for quantifying uncertainty. In data science, it is indispensable for understanding the likelihood of events, building robust statistical models, and making informed decisions when faced with incomplete information. Key concepts include probability distributions, which describe the possible values a random variable can take, and how often they occur. Understanding these distributions, such as the normal, binomial, and Poisson distributions, is vital for many analytical tasks. They help in modeling real-world data patterns effectively. Concepts like conditional probability, Bayes' theorem, and the law of large numbers are also crucial. Conditional probability helps assess the likelihood of an event occurring given that another event has already occurred. Bayes' theorem provides a way to update probabilities based on new evidence, forming the backbone of Bayesian inference and many machine learning algorithms. The law of large numbers explains how the average of results obtained from a large number of trials should be close to the expected value. These theoretical underpinnings allow data scientists to interpret model outputs, evaluate risks, and design experiments with statistical rigor. They are essential for predictive modeling. Data collection and acquisition. Data collection and acquisition represent the initial critical steps in any data analytics project, involving the systematic gathering of relevant information from various sources. This stage requires careful planning to ensure the data collected is accurate, complete, and suitable for the intended analysis. Common methods include surveys, experiments, observations, and accessing existing databases or public datasets. The choice of method depends heavily on the research question, available resources, and the type of data required. Ethical considerations, such as data privacy and consent, are paramount during this phase. Ensuring data quality at the source minimizes issues later in the pipeline. Sources of data can be broadly categorized into internal and external. Internal data originates within an organization, such as sales records, customer transaction histories, or operational logs. External data comes from outside the organization and can include market research reports, social media feeds, public government datasets, or third-party data providers. Web scraping and APIs, application programming interfaces, are increasingly popular techniques for acquiring external data programmatically. Understanding the different data sources and acquisition techniques is crucial for building comprehensive datasets for analysis. This diversity of sources enriches analytical possibilities. Data cleaning and preprocessing. Data cleaning and preprocessing are vital steps in the data analytics pipeline, often consuming a significant portion of a data analyst's time. Raw data is rarely perfect. It frequently contains errors, inconsistencies, missing values, and outliers that can severely impact the accuracy and reliability of analytical results. The goal of this stage is to transform raw data into a clean, consistent, and usable format suitable for modeling and analysis. This involves identifying and rectifying various data quality issues. Thorough cleaning ensures that subsequent analyses are based on sound data. It is a meticulous and iterative process. Common pre-processing tasks include handling missing data through imputation or deletion, detecting and treating outliers using statistical methods, and correcting inconsistencies in data entry or formatting. Data transformation techniques, such as normalization or standardization, are applied to scale features to a comparable range, which is crucial for many machine learning algorithms. Feature engineering, another important aspect, involves creating new variables from existing ones to improve model performance. These steps ensure that the data is not only clean, but also optimized for the specific analytical tasks ahead. Effective pre-processing significantly enhances model accuracy. Exploratory data analysis, EDA. Exploratory data analysis, EDA, is a critical step in the data analytics process, involving the initial investigation of data to discover patterns, detect anomalies, test hypotheses, and check assumptions with the help of summary statistics and graphical representations. It is a detective-like approach, where analysts delve into the dataset to understand its structure, relationships between variables, and potential issues. EDA helps in gaining a deeper understanding of the data before formal modeling begins. This iterative process often reveals unexpected insights. It guides the selection of appropriate analytical techniques. Key techniques in EDA include calculating descriptive statistics, such as mean, median, standard deviation, and quartiles to summarize data distributions. Visualizations like histograms, box plots, scatter plots, and correlation matrices are extensively used to identify trends, outliers, and relationships between variables. For instance, a scatter plot can reveal a linear relationship between two variables, while a histogram can show the distribution shape of a single variable. EDA is an iterative process where initial findings can lead to new questions and further exploration, ultimately informing feature engineering and model selection. It is crucial for effective problem framing. Data visualization principles. Data visualization is the graphical representation of information and data, playing a crucial role in communicating complex insights effectively and efficiently. The primary goal is to make data more accessible, understandable, and actionable for a wide audience, including non-technical stakeholders. Effective visualizations can reveal patterns, trends, and outliers that might be hidden in raw numerical data. Choosing the right type of chart or graph is paramount to conveying the intended message without distortion. Poor visualization can mislead or confuse the audience. It transforms abstract numbers into tangible stories. Several key principles guide effective data visualization. Clarity ensures that the visual is easy to understand, avoiding clutter and unnecessary elements. Accuracy demands that the visualization faithfully represents the data without misrepresentation. Relevance focuses on presenting only the information pertinent to the message. Simplicity advocates for straightforward designs that do not overwhelm the viewer. Interactivity in modern dashboards allows users to explore data dynamically. Consistency in design elements, such as colors and fonts, enhances readability and professionalism. Adhering to these principles helps create compelling and impactful data stories. They ensure the message resonates with the audience. Relational databases and SQL. Relational databases are a cornerstone of data storage and management, organizing data into tables with predefined schemas. Each table consists of rows and columns, where rows represent individual records and columns represent attributes. The relationships between these tables are established using primary and foreign keys, ensuring data integrity and consistency. This structured approach allows for efficient storage, retrieval, and manipulation of large volumes of data. Understanding relational database concepts is fundamental for any data professional. They provide a reliable framework for data management. SQL is the standard language for interacting with them. SQL, structured query language, is the standard language used to communicate with and manipulate relational databases. It enables users to perform various operations, including querying data, select, inserting new records, insert, updating existing data, update, and deleting records, delete. Advanced SQL features include joins for combining data from multiple tables, subqueries for complex data retrieval, and aggregate functions for summarizing data. Proficiency in SQL is a highly sought-after skill in data analytics, as it is essential for extracting, transforming, and loading ETL data for analysis. Mastering SQL is crucial for data manipulation. NoSQL databases, often referred to as not only SQL, represent a diverse family of database management systems that differ from traditional relational databases in their data models and scalability approaches. They are designed to handle large volumes of unstructured, semi-structured, and polymorphic data, which relational databases often struggle with. NoSQL databases offer flexible schemas, allowing for easier adaptation to evolving data requirements and rapid development cycles. They are particularly well-suited for applications requiring high availability, horizontal scalability, and fast read-write operations. This flexibility makes them ideal for modern web and mobile applications. There are several types of NoSQL databases, each optimized for different use cases. Document databases like MongoDB store data in flexible, JSON-like documents. Key value stores, such as Redis, are simple databases that store data as a collection of key value pairs. Column family stores, like Cassandra, organize data into columns and rows, but with a flexible schema across rows. Graph databases, like Neo4j, are designed to store and navigate relationships between data entities. Understanding these different models helps in choosing the right database solution for specific data analytics challenges, especially with big data. They offer alternatives to traditional relational structures. Programming for data analytics. Python. Python has emerged as the dominant programming language for data analytics and data science due to its simplicity, extensive libraries, and vibrant community support. Its readable syntax allows data professionals to focus more on problem-solving rather than intricate coding details. Python's versatility extends from data manipulation and analysis to machine learning, deep learning, and web development. This makes it a powerful, all-in-one tool for various stages of the data analytics pipeline. Learning Python is an essential skill for aspiring data analysts. Its ecosystem is continuously growing and improving. Key Python libraries are indispensable for data analytics tasks. Pandas provides high-performance, easy-to-use data structures and data analysis tools, particularly for tabular data. NumPy offers powerful n-dimensional array objects and sophisticated functions for numerical computing. Matplotlib and Seaborn are widely used for creating static, interactive, and animated visualizations. Scikit-learn is a comprehensive library for machine learning, offering tools for classification, regression, clustering, and more. Mastering these libraries enables efficient data processing, insightful analysis, and robust model building. They form the backbone of Python-based data science workflows. Programming for data analytics, R. R is another powerful programming language and environment widely used for statistical computing and graphics, particularly favored by statisticians and researchers. It provides a vast collection of packages specifically designed for statistical modeling, data manipulation, and high-quality data visualization. R's strength lies in its ability to perform complex statistical analyses with relatively few lines of code. It offers a rich environment for statistical experimentation and academic research. While Python is more general purpose, R excels in deep statistical exploration. Its community is highly specialized in statistics. Key R packages are essential for data analytics tasks. dplyr and tidyr are part of the tidyverse and provide powerful tools for data manipulation and cleaning. ggplot2 is renowned for creating elegant and highly customizable data visualizations. Caret, classification and R regression training, offers a consistent interface to many machine learning algorithms. Forecast is specifically designed for time series analysis and forecasting. Learning R complements Python skills, providing a different perspective and specialized tools for statistical rigor. It is particularly valuable for academic and research-oriented data analysis. These packages enhance R's capabilities significantly. Alt. Machine learning fundamentals. Machine learning is a subfield of artificial intelligence that enables systems to learn from data, identify patterns, and make decisions with minimal human intervention. Instead of being explicitly programmed, machine learning algorithms build a model from example data, known as training data. This model then makes predictions or decisions without being specifically programmed for every possible scenario. Understanding the core concepts of machine learning is crucial for advanced data analytics, as it allows for predictive modeling and automated insight generation. It represents a significant leap in data-driven capabilities. The field is rapidly evolving with new techniques. Machine learning algorithms are broadly categorized into supervised and unsupervised learning. Supervised learning involves training a model on labeled data, where the input and corresponding output are known. This includes tasks like classification, predicting categories, and regression, predicting continuous values. Unsupervised learning deals with unlabeled data, aiming to find hidden patterns or intrinsic structures within the data. Clustering grouping similar data points, and dimensionality reduction are common unsupervised tasks. There is also reinforcement learning, where an agent learns to make decisions by performing actions in an environment to maximize a reward. Each paradigm serves different analytical objectives. These distinctions are fundamental to selecting the right approach. Regression analysis. Regression analysis is a powerful statistical method used to model the relationship between a dependent variable and one or more independent variables. Its primary goal is to understand how the value of the dependent variable changes when any one of the independent variables is varied, while the other independent variables are held fixed. This technique is widely applied in predictive modeling, forecasting, and determining cause and effect relationships. For instance, it can predict house prices based on features like size and location, or sales based on advertising spend. Understanding its principles is crucial for quantitative analysis. It helps in making informed predictions. Two common types of regression are linear regression and logistic regression. Linear regression is used when the dependent variable is continuous, aiming to find the best-fitting straight line that describes the relationship between variables. Logistic regression, despite its name, is used for classification problems, where the dependent variable is categorical, e.g., binary outcomes like yes or no. It models the probability of a certain class or event occurring. Both methods involve fitting a model to training data and then using that model to make predictions on new, unseen data. Understanding when to apply each type is key to accurate analytical outcomes. They are foundational in predictive modeling. Classification techniques. Classification is a supervised machine learning task that involves categorizing data into predefined classes or labels. The goal is to build a model that can predict the class of new, unseen data points based on patterns learned from labeled training data. This technique is widely used in various applications, such as spam detection, spam or not spam, medical diagnosis, disease or no disease, and sentiment analysis, positive, negative, or neutral. Effective classification models are crucial for automating decision-making processes and filtering information. It is a core component of many AI systems. The accuracy of these models is paramount. Several powerful algorithms are commonly employed for classification tasks. Decision trees make decisions by splitting data based on features, forming a tree-like structure of choices. Support vector machines, SCMs, find an optimal hyperplane that best separates data points into different classes. K-nearest neighbors, KNN, classifies a data point based on the majority class of its K closest neighbors in the feature space. Other methods include naive Bayes, random forests, and gradient boosting. Each algorithm has its strengths and weaknesses, and the choice often depends on the nature of the data and the specific problem. Understanding these techniques enables robust predictive modeling. They are essential for categorical predictions. Clustering algorithms. Clustering is an unsupervised machine learning task that involves grouping a set of data points such that data points in the same group or cluster are more similar to each other than to those in other groups. Unlike classification, clustering does not rely on predefined labels. Instead, it discovers inherent structures or patterns within the data. This technique is widely used for market segmentation, anomaly detection, document analysis, and image processing. It helps in identifying natural groupings in datasets where labels are unknown or difficult to obtain. Clustering is a powerful tool for exploratory data analysis. It reveals hidden relationships within data. Two prominent clustering algorithms are k-means and hierarchical clustering. K-means clustering partitions data into k distinct clusters where k is a user-defined number by iteratively assigning data points to the nearest centroid and updating the centroids. Hierarchical clustering builds a hierarchy of clusters, either by starting with individual data points and merging them, agglomerative, or by starting with one large cluster and splitting it, divisive. The choice of algorithm depends on the data structure, the desired number of clusters, and the interpretability requirements. Evaluating cluster quality often involves metrics like silhouette score or inertia. These algorithms are fundamental for discovering latent groups in data. They provide valuable insights into data structure. Time series analysis. Time series analysis is a specialized branch of data analytics focused on analyzing data points collected sequentially over time. Unlike traditional datasets where observations are independent, time series data exhibits temporal dependencies, meaning past values can influence future values. The primary goals of time series analysis include understanding the underlying structure of the data, identifying patterns like trends, seasonality, and cycles, and ultimately forecasting future values. This technique is critical in fields such as finance, economics, weather forecasting, and demand planning. It helps in predicting future events. Understanding temporal patterns is key. Key components of time series data include trend, seasonality, and irregular components. Trend refers to the long-term increase or decrease in the data over time. Seasonality describes patterns that repeat over a fixed period, such as daily, weekly, or yearly cycles. Irregular components are random fluctuations that cannot be explained by trend or seasonality. Common techniques for time series analysis include moving averages, exponential smoothing, ARIMA, autoregressive integrated moving average models, and more advanced methods like profit or LSTM neural networks. Effective time series analysis requires careful handling of temporal dependencies and selection of appropriate models. It is essential for accurate forecasting. Natural language processing (NLP) basics. Natural language processing (NLP) is a subfield of artificial intelligence that focuses on enabling computers to understand, interpret, and generate human language. It bridges the gap between human communication and computer comprehension, allowing machines to process and analyze vast amounts of text data. NLP is at the core of applications like sentiment analysis, spam detection, language translation, and chatbots. As text data constitutes a significant portion of available information, NLP skills are increasingly valuable for data analysts. It unlocks insights from unstructured text. The field combines linguistics, computer science, and AI. Fundamental NLP tasks include tokenization, stemming, lemmatization, and part-of-speech tagging. Tokenization breaks down text into individual words or phrases, tokens. Stemming and lemmatization reduce words to their root form, handling variations. Part-of-speech tagging identifies the grammatical role of each word. More advanced techniques involve named entity recognition, identifying proper nouns, sentiment analysis, determining emotional tone, and topic modeling, discovering abstract topics. Libraries like NLTK and SpaCy in Python provide robust tools for these tasks. Understanding these basics is crucial for extracting meaningful information from unstructured text data. They form the building blocks for text analytics. Big data technologies. Big data refers to datasets so large and complex that traditional data processing applications are inadequate to deal with them. It is characterized by the 3 V's: volume, immense amounts of data; velocity, high speed of data generation and processing; and variety, diverse types of data, both structured and unstructured. Big data technologies provide the tools and frameworks necessary to store, process, and analyze these massive datasets efficiently. Understanding these technologies is crucial for handling modern data challenges. They enable scalable data solutions. The ability to manage big data is a key differentiator. Key big data technologies include Hadoop and Spark. Apache Hadoop is an open-source framework that allows for distributed storage and processing of large datasets across clusters of computers. Its core components are HDFS, Hadoop Distributed File System for storage, and MapReduce for processing. Apache Spark is an open-source, unified analytics engine for large-scale data processing. Known for its speed and ease of use, it can run on Hadoop, Kubernetes, standalone, or in the cloud, offering faster processing due to in-memory computation. These technologies enable organizations to extract valuable insights from colossal datasets that would otherwise be unmanageable. They are foundational for scalable data analytics. Mastering them is essential for big data professionals. Cloud platforms for data analytics. Cloud platforms have revolutionized data analytics by providing scalable, flexible, and cost-effective infrastructure for storing, processing, and analyzing vast amounts of data. Instead of managing physical servers and hardware, organizations can leverage cloud services on demand, paying only for the resources they consume. This eliminates the need for large upfront investments and allows businesses to scale their analytics capabilities rapidly in response to changing needs. Major cloud providers offer a comprehensive suite of data analytics services, from data warehousing to machine learning. Cloud adoption is accelerating across industries. It democratizes access to powerful tools. Leading cloud providers like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP, offer specialized services for data analytics. AWS provides services like Amazon S3 for storage, Amazon Redshift for data warehousing, and Amazon SageMaker for machine learning. Azure offers Azure Data Lake Storage, Azure Synapse Analytics, and Azure Machine Learning. GCP features Google Cloud Storage, BigQuery for data warehousing, and AI Platform for machine learning. Understanding the offerings of these platforms is crucial for designing and deploying scalable data analytics solutions in the cloud. They provide robust ecosystems for modern data professionals. Choosing the right platform depends on specific project requirements. Data storytelling and communication. Data storytelling is the art of communicating insights from data in a compelling and understandable narrative, transforming complex analyses into actionable information. It involves combining data, visuals, and narrative to engage an audience and drive decision-making. Simply presenting charts and numbers is often insufficient. A well-crafted story provides context, explains implications, and persuades stakeholders. Effective data storytelling bridges the gap between technical analysis and business understanding. It ensures that the hard-won insights resonate with the audience. This skill is critical for data analysts to maximize their impact. Key elements of effective data storytelling include understanding the audience, defining the core message, and structuring the narrative. Knowing the audience's background and needs helps tailor the complexity and focus of the story. A clear, concise core message should be established early and reinforced throughout the presentation. The narrative structure typically follows a logical flow: problem, data exploration, insights, and recommendations. Using appropriate visualizations, clear language, and a compelling storyline are crucial for making data memorable and impactful. Practicing presentation skills and anticipating questions also contributes to successful communication. It transforms data into a persuasive argument. Ethical considerations in data analytics. Ethical considerations are paramount in data analytics, guiding how data is collected, stored, analyzed, and used to ensure fairness, privacy, and responsible practices. The immense power of data comes with significant responsibilities, as misuse or biased application can lead to harmful consequences for individuals and society. Data analysts must navigate complex ethical dilemmas, balancing the pursuit of insights with the protection of individual rights and societal well-being. Ignoring these considerations can result in legal repercussions, reputational damage, and erosion of public trust. Ethical frameworks are essential for responsible data handling. It's a critical aspect of professional conduct. Key ethical concerns include data privacy, algorithmic bias, and transparency. Data privacy involves protecting sensitive personal information and ensuring compliance with regulations like GDPR and CCPA. Algorithmic bias occurs when machine learning models produce unfair or discriminatory outcomes due to biased training data or flawed algorithms. Transparency requires explaining how models make decisions, especially in critical applications. Other concerns include data security, informed consent, and the potential for surveillance. Data professionals must actively work to mitigate these risks by implementing ethical guidelines, conducting bias audits, and prioritizing privacy-preserving techniques. A proactive approach to ethics is vital. It ensures data is used for good. Deployment and MLOps machine learning operations are crucial stages in the machine learning lifecycle, focusing on taking trained models from development to production environments and maintaining them effectively. Model deployment involves integrating a machine learning model into an existing system or application so it can start making real-time predictions or decisions. This transition from experimental code to operational software requires careful planning and robust engineering practices. Without proper deployment, even the most accurate models remain academic exercises. It ensures models deliver tangible business value. This stage bridges the gap between data science and software engineering. MLOps extends DevOps principles to machine learning, encompassing practices for continuous integration, continuous delivery, and continuous training of models. It involves automating the entire machine learning workflow, from data collection and model training to deployment, monitoring, and retraining. Key aspects of MLOps include version control for data and models, automated testing, infrastructure provisioning, and performance monitoring of deployed models. Monitoring is particularly important to detect model drift or degradation over time, triggering retraining when necessary. MLOps ensures reliability, scalability, and maintainability of machine learning systems in production. It is essential for long-term model success. Advanced analytics techniques. Beyond foundational machine learning, advanced analytics encompasses more sophisticated techniques that address complex problems and leverage larger, more intricate datasets. This includes areas like deep learning, which utilizes artificial neural networks with multiple layers to learn complex patterns from data. Deep learning has achieved remarkable success in fields such as image recognition, natural language processing, and speech recognition. Understanding these advanced techniques allows data analysts to tackle cutting-edge challenges and extract deeper insights. It pushes the boundaries of what is possible with data. The computational demands are often higher. Other advanced techniques include reinforcement learning, which focuses on training agents to make sequential decisions in an environment to maximize a cumulative reward. This is particularly relevant for robotics, game-playing, and autonomous systems. Ensemble methods, such as random forests and gradient-boosting machines, combine multiple models to improve predictive performance and robustness. Anomaly detection, graph analytics, and causal inference are also part of advanced analytics, each offering unique capabilities for specific problem domains. Exploring these methods expands an analyst's toolkit significantly. They provide solutions for highly specialized problems. Capstone project planning. The Capstone project is a culminating experience in the Advanced Diploma in Data Analytics, providing students with the opportunity to apply all learned skills to a real-world problem. This project allows learners to integrate theoretical knowledge with practical application, from data acquisition and cleaning to modeling, visualization, and communication of insights. It typically involves selecting a relevant dataset or business problem, defining objectives, and executing a complete data analytics lifecycle. The Capstone project demonstrates proficiency across the entire data analytics spectrum. It is a critical component for portfolio building. Careful planning is essential for success. Effective capstone project planning involves several key steps. Project selection. Choose a topic that is personally interesting and has accessible data. Problem definition. Clearly articulate the business problem, objectives, and success metrics. Data strategy. Plan for data acquisition, cleaning, and pre-processing. Methodology. Select appropriate statistical and machine learning techniques. Tooling. Identify the programming languages, Python, R, libraries, and platforms, cloud, local, to be used. Timeline and deliverables. Establish a realistic schedule and define expected outputs, such as reports, presentations, and deployed models. Thorough planning ensures a structured approach and increases the likelihood of a successful and impactful project. It prepares students for real-world project management. Career paths in data analytics. The field of data analytics offers a diverse range of exciting and high-demand career paths, reflecting the increasing reliance of industries on data-driven decision-making. Professionals with an advanced diploma in data analytics are well-positioned for various roles that require analytical thinking, technical skills, and business acumen. The demand for data talent continues to grow exponentially across sectors like technology, finance, healthcare, and marketing. Understanding the different career options helps individuals tailor their skill development and job search strategies. This diploma opens doors to numerous opportunities. It prepares graduates for impactful roles. Common career paths include data analyst, business intelligence, BI analyst, data scientist, machine learning engineer, and data engineer. Data analysts focus on extracting insights from data to support business decisions, often using SQL and visualization tools. BI analysts specialize in creating dashboards and reports to monitor business performance. Data scientists build predictive models and develop advanced algorithms. Machine learning engineers design, build, and deploy ML systems. Data engineers build and maintain the infrastructure for data pipelines. Each role requires a unique blend of technical expertise, problem-solving abilities, and communication skills, offering diverse opportunities for specialization and growth. The industry is dynamic and constantly evolving.